In this video we're going to see bode plot of 0 on real axis, and the function for a 0 on real axis looks like this: 1 plus st. Now for frequency analysis we substitute s with j omega, right? And we look at magnitude and phase as omega is varied from 0 to infinity. Now the 0 of this one is when s equals minus 1 over t. Okay, and now if we point this out on a s-plane where real axis is represented with sigma and imaginary j omega, we represent it here. Okay, minus 1 over t. Zeros we represent with a circle on the s-plane. Okay, now here we assume t is positive, so that's the reason why we represented negative half of the s-plane. Now the function to look at is 1 plus j omega t. Now for j omega t we can write magnitude as square root of 1 plus omega square t square and phi as tan inverse of omega t, right? And if you want to write magnitude in dB, that's what we'll be interested in. We write it as 20 log base 10 of square root of 1 plus omega square t square. Now in this we'll have two conditions. Okay, when omega t is less than 1, okay, and when, okay, let's see the first condition first. When omega t is less than 1, omega square t square will be very less than 1. In that case we can write 1 plus omega square t square as 1 itself. So square root of 1 is 1, and we can write 20 log base 10 of 1 as 0 dB. Okay, the magnitude is going to be 0 dB. Now if we have a second condition where let's take omega t is greater than 1, in that case omega square t square will be much larger than 1. In that case we can neglect 1 here, okay, in this term, and we can write this term as square root of omega square t square, fine. And we can write this as effectively omega square t square square root, which is nothing but omega t. So we can write this magnitude as 20 log base 10 of omega t, fine. And now let's see, when omega t is greater than 1, we are saying let's take omega t is 10, okay, and let's pick some other values, let's say 100. In that case the magnitude in dB is going to be, for this it is going to be 20 dB, because log base 10 of 10 is going to be 20, so it is 20 dB, and for 100 it is 40 dB, and if you see for 1000 it is going to be 60 dB. Now from this we can see 10 to 100 it is 1 decade, and 100 to 1000 it is 1 decade. Per decade it is increasing by 20 dB. Okay, 10 to 100 it is increasing by 20 dB, and 100 to 1000 it is increasing by 20 dB. So now when omega t is less than 1 it is 0 dB. Now if we take a plot where y is in dBs, linear scale dB, and x is in log of omega, and let's take this point when omega's corresponding value is 1 over t, and this omega's corresponding value is 10 over t, and this 100 over t. Okay, and now let's take this as 0 dB, 20 dB, 40 dB, and 60 dB. Let's take 80 also, 80 dB. Okay, now when omega t is less than 1 in this region it is going to be 0 dB. Okay, as we have seen before that these bode plots are asymptotic plots, so we take this omega t less than 1 continuous to this point, and then when omega t is 10, where omega equals 10 over t, it is 20 dB, and for this point when omega t is 100, where omega is 100 over t, it is 40 dB. In that case this plot is going to be a straight line like this, okay, which is increasing at a rate of 20 dB per decade. 20 dB per decade. As we have seen before, it can be also written as 6 dB per octave. Octave we meant omega 2, the higher frequency divided by the lower frequency. If it is equal to 2, then we say these two frequencies have an octave. Suppose if I take this point, suppose say 2 by t, then this value here is going to be, corresponding value for this 2 by t is going to be 6 dB. It means it is increasing 6 dB per octave. So omega equal to 1 by t to 2 by t is 1 octave. 2 by t to 4 by t is another octave. Okay, so this is how the bode plot looks for a 0 at real axis, okay, on S-plane. Now if let's try plotting the phase plot for this. Okay, now let's take the same axis, but let's take x as log of omega and y in phase degrees. Let's take 0, 90 degrees, 180 degrees. Now we know the formula for phi of omega, which is nothing but tan inverse of omega t. When omega t equals 1, the phi is 45 degrees. Okay, when omega t tending to infinity, phi is going to 90 degrees, and when omega t is approximately 0, the phi is approximately 0. Okay, now let's take this point omega equals 1 by t. At that point, if you take 45 degrees, it is going to be 45 degrees, right? And it reaches 90 degrees as omega tends to infinity, fine. And it is 0 when omega is 0, but we don't take 0 values usually on log plot, because log of 0 is not defined, or it goes to minus infinity kind of. Let's take this plot. Okay, the plot looks like this. It will be 45 degrees when omega equals 1 by t, and it is approximately 0 when for a very small values of omega, and it tends to 90 degrees plus 90 degrees as it is a 0 in the case of phase. Okay, it's going to be plus 90 now. And we have seen previously omega equals 1 by t is known as corner frequency. Okay, corner frequency. Now let's look at a function, okay, which has 1 plus j omega t whole square. It means there are two zeros on the real axis of S-plane which have the same corner frequency. The corner frequencies are same. Okay, now looking at this from the previous experience we had, from the previous videos, we have seen if we have two poles, we saw how it is changing. So similarly, from this we can say when omega equals 1 by t, it is going to be 0 dB, and less than that it will be 0 dB. But let me pick a different color to differentiate this. Okay, it is going to be 0 dB till omega less than 1 by t, and when omega equals 10 by t, it is going to be 40 dB. Okay, let me draw this. And when omega equals 100 over t, it is going to be 80 dB. Okay, it's going to be 80 dB. This is the plot for the function of 1 plus j omega t whole square. The corner frequency remains the same, where omega equals 1 by t, and the slope of this one is 40 dB per decade, or we can write this as 12 dB per 12 dB per octave. Okay, and if you go and look at the phase plot, how it looks, phase we can write this as phi of omega equals 2 times tan inverse of omega t. Now when omega equals 1 by t, when it means omega t is 1, then it will be 90 degrees, and as omega, okay, let me write it here. When omega t equals 1, it is going to be 90 degrees. As omega t tends to infinity, it is going to be 180 degrees, and omega t values, very less values, it's going to be nearly 0. So in this case, let's take 180 here reference, how it is going to change. And at omega equals 1 by t, it is going to be 90 degrees. And let's draw the plot. It's going to be like this. Okay, this plot is corresponding to 1 plus j omega t, that is one single pole on the real axis, and this is for corresponding to two single poles with the same corner frequency on the real axis. Okay,